Hello everyone, welcome to the week 3 of this NPTEL course Solar Energy Engineering and Technology Problem Solving session. So, in the today's lecture we are going to see how to estimate the solar radiations at various angles. Previously we studied about various angles like zenith angle, solar altitude angle, solar azimuth angle, surface azimuth angle, and their inclination. And so the various angles were the latitude, zenith angle, solar altitude angle, angle of the incidence, surface azimuth angle, and the solar azimuth angle, declination angle, hour angle. So in this session, we are going to study that how to estimate the solar radiations. So why the question is why we need to estimate first the solar radiation. So detailed information may be available about solar radiation at any location, and that is essential for designing and valuation to assess the economic viability of any kind of solar energy system. So if we see the solar spectrum, we can see that we get a large fraction of the UV visible and the infrared spectrum, and so there are two things comes. One is the solar irradiance, the solar radiation that falls over the surface, and another thing is the uh, particularly the solar constant. So the incident solar radiation, that is also called as the we have to estimate the incident solar radiation, that is also called as insolation, and it is measured in terms of the irradiance or the energy per unit area or per unit time. So, and the energy per unit area will be per unit time will be the power. So, this will be power per unit area. So, we have to estimate the what is the overall the irradiance, and then we will study about the solar irradiance at various surfaces, at horizontal surface, at tilted surface, at extraterrestrial surface, and at terrestrial site. So, the first thing we discuss about extraterrestrial solar radiations. So the extraterrestrial solar radiation means outside of the Earth surface. So we have to first clear about the solar constant. So solar constant is the average amount of the solar radiation falling on a surface normal to the rays of the sun outside the atmosphere of the Earth at mean Earth Sun distance. This is the sun, this is the Earth. If you see the mean Earth Sun distance, so at this mean Earth Sun distance, we have to calculate the solar constant. So generally, the value is the 1367 watt per meter square, though it varies slightly based on the different assumption and the consideration and calculations. Then once we know the solar constant, then we can easily calculate the extraterrestrial radiation. The extraterrestrial radiation is I is equal to I naught into D naught by D. D naught and D are the radius of the diameter of the sun and the earth respectively. So if we we can convert it into the form of I is equal to I naught 1 plus 0.034 cos 360 n divided by 360.25, and the n will be the number of the days. For suppose January 1, so n will be 1 for January 1. Likewise for January 10, n is equal to 10, and for January 31, n is equal to 31, and if we say February 1, so the value of for the February 1 will not be 1, it will be 31 plus 1. It will be 32. So similarly for August 8, the value of n is equal to 31 days in and 28 or 29 days based on the leap year in February, 31 days in January, then February, March, April, May, June, July, then the 8th August on the August. So this way we will calculate the value for the n. So once we know the solar radiation on the extraterrestrial surface, then it comes solar radiation on the terrestrial surface. So we can divide the whole system into two parts. One is the terrestrial and another is the extraterrestrial. So while the solar radiation will fall from sun to any surface, it will pass through the atmosphere. The atmosphere will be having the cloud, the dust particles and other that may refract and scatter the solar radiations. So in this way we generally obtain solar radiation in two form. One is the beam radiation that we get directly from sun to the surface, and another is the diffuse radiation that passes through any object in the atmosphere. So that is a diffuse radiation. So while calculating the terrestrial solar radiation, we have to consider the beam radiation and diffuse radiation as well. So beam normal solar radiation for solar zenith angle of Z, the correlation is given I exponential of minus km, where m is the air mass ratio, and air mass ratio is can be calculated basically by the m is equal to bp, the solar radiation crossing through the atmospheric surface, divided by ap when the sun will be at the zenith. Uh, so bp by ap is equal to 1 by cos z is equal to 1 by sine alpha. So or another correlation for to calculate the accurate value of m is given, m is equal to 1 upon sine alpha 0.50572 into 6.07995 plus alpha to the power minus 16364. So that will give the most accurate value for the m. So once we know the value for the IBN, B normal solar radiation, that can be calculated based on the beam and diffuse optical depths tau b and tau t, and IDH is the diffuse horizontal irradiance per unit area on a horizontal surface. And here we see the value of the B and D, these are the constants, and the air mass exponents E, B and D can be correlated with the tau B and the tau T. So finally solar radiation on a horizontal surface will be summation of beam normal radiation and diffuse radiation. Then after coming then after horizontal surface, another is the what is the tilted surface. Like this is the surface and here we have object like this or solar panel, so or any other kind of the tilted surface. So how we will calculate the solar radiation on the tilted surface? So it will be summation of the beam radiation, diffuse radiation and on the radiation on the over the ground. So IBC is calculated. So for this we have to calculate three functions: IBC, IDC, and IRC. IBC is the function of IBN normal beam radiation into cos I. Cos I can be calculated based on the various angles related to various solar angles like cos alpha. Alpha is solar altitude angle, AS, and AW. AS is your solar azimuth angle, and AW is the panel azimuth angle or surface azimuth angle. Then sine beta, beta is the tilt, the slope is given, and the alpha is the solar altitude angle. So once we know, so to calculate the tilted beam radiation on a tilted surface, we should know at least these angles: solar altitude angle, then solar azimuth angle, surface azimuth angle or panel azimuth angle, tilted angle is given, and the incident angle. So we have to calculate. Once we calculate the IBC, then we can calculate the value for the IDC. IDC is based on the IDH, and it is generally the only the tilt angle we should know for this. And then comes the ground reflected solar radiation, IRC. IRC is a function of rho beam normal radiation, solar altitude angle, and the tilt angle. So let's understand the applications of these different angles in calculating the radiation over a surface. So the question says find the instantaneous solar radiation at 12 known EST. So 12 known local standard time LST is given on a solar collector surface. Beta is given 30 degree. Panel azimuth angle or surface azimuth angle 10 degree is given on February 1 in Tampa, Florida, and the location is given. For these two for these location, the value of the tau b and tau d are given. So tau d and tau b, I will show you here. The value of the tau b and tau d will be used to calculate the beam normal irradiance and diffuse horizontal irradiance. And another is the latitude is given 27.96 L. That L local is given 82.54 and LST 75 watt is given. So L local is the longitude of the given location that we will discuss in detail in later, and LST is the standard meridian for the local time zone. Okay, so the problem is we have to use the formula to calculate the instantaneous solar radiation. Then how to solve it? IC, IBC, IDC, and IRC. IBC we know that is a function of solar incidence angle and beam normal radiation. So for that we have to calculate IBN and cos I. Then for cos I we have to calculate cos I can be calculated using cos alpha into cos alpha s minus AW sin beta sin alpha cos beta. Only beta is given 30 degree and AW is given 10 degree. We have to calculate AS. We have to calculate cos alpha and cos AS. Cos alpha is the solar altitude angle. Then how to calculate the solar altitude angle first? And one is the solar alpha we have to calculate. Alpha S we have to calculate. Next come IDC. IDC is a function of IDH cos beta, and beta is given IDH can be calculated, and IRC is function of IH total solar irradiance and cos beta and rho. Okay, so let's calculate first solar altitude angle and solar azimuth angle. So solar altitude angle sin alpha is function of the solar declination angle and the hour angle. So hour angle can be calculated based on the solar time HS is equal to ST minus 12 15 degree per hour, and solar time can be calculated based on the LST ET. ET is the equation of time, LST longitude of the given location, and L local longitude of the given location. LST is the standard meridian for the local time zone. So based this, first we have to calculate the ST, and then we will be able to calculate the hour angle. So one thing is for solving any numerical, we have to know what the particular parameters are required. So first we have to solve the we have to calculate the particular parameter, the values for this particular parameter. So once we will be able to calculate the solar time, then we can able to calculate the hour angle. For based on the hour angle, we will be able to calculate the value for the sin alpha, solar altitude angle alpha. And another thing we need the value for the delta S, and for the to calculate the solar azimuth angle also we need the value for the delta S and the HS. Delta S is the solar declination angle. Solar declination angle can be calculated based on the 23.45 degree sine 360 to 84 plus n divided by 365. N is again the number of the days. Okay, so let's calculate first the declination angle. So for February 1 is given, so n will be 31 plus 1, 32, and then the declination angle will be minus 17.51 degree. Once we know the declination angle, another thing we should know the equation of time. For the equation of time, we have to calculate the value for the B. B is 360 n minus 81 upon 364. N is again the number of days, so it will be 32. Once we know the B, we can calculate the value for ET. ET is the equation of time, that is 9.87 into sine 2B minus 7.53 cos B and 1 minus 1.5 sine B. So the correlation is already available for all these equations. Once we know the ET, we can calculate now the value for the ST. We can calculate the value for the ST, and LST is given, local solar time is given 12 hour. Once we know the value for the ST, we can then calculate the values for the hour angle. The value of the ST is given, so our angle will be minus 11.11 degree. Our angle we know. Now we can calculate the values for the declination angle. We know minus 17.51 degree centigrade. Our angle we know minus 11.11 degree. L latitude is given 27.96. So based on this, we can calculate the value for the alpha. Alpha will be the sine inverse of this function, is equal to 43.30 degree. So alpha we know. Now we have to calculate for the solar azimuth angle, alpha S. So it will be based on the cos delta S, declination angle, and hour angle, and the altitude. So the value for the alpha S is equal to minus 14.61. One more thing is here, we have to know the absolute sign for the alpha S. What happens, you can go detail with this test. Generally the sign varies as less than 90 degrees centigrade, since alpha is equal to sine 180 minus alpha S. So the to solve this problem, there are two correlation for where latitude is greater than declination angle and latitude is less than or equal to the declination angle. So in this case, when the latitude is less than declination angle, the problem is very much pretty solved. So in this case, sun will remain in north, and if we talk about the southern hemisphere, the sun will be always be in the south. But when L is greater than delta S, then we have to calculate for T and TW. And based on the, if the TE is greater than solar time ST, the sun will be would be toward the north for the northern hemisphere and south for the southern hemisphere, and vice versa. So we have to calculate for the TE first. So here we see the value for the TE is 3.5689 hours. So and the ST we saw the value for the ST was 11 hours 16 minutes. So ST is greater than TE. So in this case, the sun will be in the south, and for the south the uh, sign will be the minus. And based on this, we can further calculate the other values. Now the next thing, we have to calculate the air mass ratio. Air mass ratio we have to calculate based on the solar altitude angles. Solar altitude angle we already calculated as 14.30 degree. So the air mass ratio will be 1.4565. Similarly, the parameters B and D we need for the to calculate the IBC and IDH. So the value for the will be based on the tau beta and the tau D. These are the corresponding depths. Then based on the based on this solar constant, we have to calculate the extraterrestrial solar radiation, and here n will be again 31 plus 1 32. So once we calculate all these value, we have to just put in the given formulas. For one formula is the direct solar radiation. We can calculate now. I we know 1406, tau beta we know, B the value for the B we know. So IBN we will get, once IBN we will get, then based on I extraterrestrial solar radiation, we can get the value for the diffuse solar radiation. Once IBN, the value for the IBN and IDH we know, so we can calculate the values for the IBC. IBC is function of IBN and cos I. So we calculated solar altitude angle, solar azimuth angle, panel azimuth angle or surface azimuth angle was given. This is tilt angle was given, and the solar altitude angle we calculated. Based on this, we will calculate the value for cos I. Once we calculate the value for the cos I and the product of IBN and cos I, we will get the value for the instantaneous beam radiation IBC on the surface per unit area. Next, come to the diffuse radiation on the collector surface. That will be the function of the IDH. So IDH, the value of the IDH we calculate from the based on the extraterrestrial solar radiation. And similarly, we calculate the ground reflected solar radiation IRC is equal to this is the function of rho, IBN and IDH. IBN, IDH we know the value for the rho is given 0.2, and based on this IRC will be 10 watt per meter square. Finally, to calculate the total radiation over a tilted collector surface, it will be the summation of the IBC, IDC and IRC, that is 932 watt per meter square. So yeah, this was a cumulative problem where we understood how to calculate the solar radiation, and not only the solar radiation on which surface, terrestrial and extraterrestrial surface, how these two are correlated, one thing. And the second thing, to calculate the terrestrial solar radiations, we need a different value for the solar and we need the different values for the solar angles. So first we have to be clear with all these formulae related to the calculation for solar angles. So if I will take it through again through the problem. Yeah. So the basic solar angles we should always know about any surface are the solar altitude angle, solar azimuth angle, surface azimuth angle, and the panel tilt angle. The panel azimuth angle and the surface azimuth angle both are the same, and the incident angle we should know. Apart from that, we should know the declination angle, we should know the hour angle. Once we are clear about all these formulae for all these things, we can easily calculate the solar radiation at terrestrial surface. So the formula for the solar altitude angle will be sin alpha is cos delta s into cos L into cos HS plus sin delta S and into sin L. For the detailed derivation of this formulae or these empirical equation, I will recommend you to follow the book Solar Energy, Principles of Thermal Collection and Storage by S.P. Sukhatma and J.K. Nayak. And other book is Principles of Solar Energy by, I will take you if through this book. This book, Principles of Solar Engineering by D. Yogi Goswami, and another book, Solar Engineering of Thermal Process by John Duffy, can be followed. Okay, coming back to the solar altitude angle. Solar altitude angle, uh, sin alpha is equal to cos delta s, cos of declination angle into cos of latitude into cos of r angle plus sin of declination angle into sin of latitude. Similarly, solar azimuth angle can be calculated based on the cos of declination angle sin of r angle upon cos alpha at solar altitude angle, and HS is calculated based on the solar time, and solar time is calculated based on the LST is given always in the question, the local standard time, and the ET will be function of the beam. Beta, again for beta we should know the number of the days. Then comes the declination angle. Declination angle we have to calculate based on the formula given, 23.45 degrees sine of 360 into 284 plus n is the number of days plus 365 divided by 365. Once we know the values for the hour angle, ST, and the declination angle, we can calculate the values for the solar altitude angle and the solar azimuth angle. And whenever we are calculating the solar azimuth angle, AS, we have to always check the sign, and for this we have to calculate the values for the TE or the TW. So if ST is greater than TE, the sign will be the negative. Then we can calculate the air mass ratio. Air mass ratio is the solar radiation crossing through the atmosphere to the surface, divided by if the sun would be at zenith. So these are the basics of the solar radiation calculation. Another term comes with how to calculate the global radiations, average of the global radiations. So many times we need the average of the daily global radiation of the or the hourly global radiation, both at the horizontal surface and the tilted surface. So for this, very basic empirical correlations are given, and though there are many empirical correlations, but the selected empirical correlation which best suits for the particular area that we have to adapt. So uh, for uh, for this particular coursework, we have adopted these solar radiations, and the details can be obtained uh, in the book by S.P. Sukhatma and J.K. Nayak, Solar Energy, Principles of Thermal Collection and Storage. And so monthly, average, daily. So we have to see carefully what is our requirement: monthly, average, daily global radiation. So we might be interested in getting the values for the daily global radiation, only the diffuse radiation, only the beam radiation, or only the scattered or the diffuse radiations. So first, let's go to monthly, average, daily global radiation. So that will be the average of the Hg upon H naught is equal to A plus B. the average of S upon average of S max. Hg is the monthly average of daily global radiation on a horizontal surface. This will be Hg, monthly average of daily global radiation on a horizontal surface. H0, monthly average daily extraterrestrial radiation on a horizontal surface. That is the required on a horizontal surface, that is on the extraterrestrial horizontal surface. A and B are the constant that are obtained by regression analysis uh, major of measured values of global solar radiation and sunshine duration, and S average is monthly average of sunshine hours per day at location, and S max is the monthly average of the maximum possible sunshine hours per day at the location. So the values for the S is generally given, and the values for the A and B, these are given for particular cities across the globe and in the Indian context as well. So let's see the another thing, the monthly average daily global radiation. We know monthly average daily global radiation, we have to calculate Hg upon, that is the monthly Hg is the monthly average of daily global radiation on a horizontal surface, that we have to require, and the correlation to calculate is divided by H0. H0 is the monthly average daily global radiation on extraterrestrial surface is equal to A plus B, the regression values, into S divided by S max. S is the average monthly average of the sunshine hours per day, and S max is the monthly average of the maximum possible sunshine hours per day. These are the total day length on the horizontal surface. So to calculate the H0, it is calculated based on the solar constant and the number of the days, and for this again we should know the values for the hour angle, latitude, declination angle. So the hour angle can be calculated based on the latitude and the declination angle. So once we know the hour angle, we can calculate the S max also, 2 by 15 into omega S, and the declination angle we know 23.45 into sine of 360 divided by 365 into 284 plus n. Okay, so let's understand how to use these different formulas to calculate our requirement, particularly we are looking for the monthly average daily global radiation. So it's said the estimate the monthly average daily global radiation on a horizontal surface at Vadodara. The latitude is given during the month of March if the average sunshine hours per day is 9.5, and EL is also given 34 meter. So the EL is not required here. Okay, so the okay, so how to solve it? The equation we know to solve it is H average of Hg, that we have to calculate, upon H naught is equal to A plus B, average of the daily sunshine hours and the average of the maximum daily sunshine hour, and so the value of the A and B we can get from the given table. For Vadodara, we can take the 0.28 and 0. It will be in Ahmedabad, so 0.28 and 0.48. Now next we have to calculate this was here. Hmm. If the average sunshine hours is given, so we know this thing. So now we have to calculate H naught. H naught we can calculate based on the function ISC 24 upon pi into solar constant into 1 plus 0.33 cos 360 and divided by 365, and is the number of days into latitude. Latitude is given 22. So latitude is given 22 degree. Omega is not given. Our angle we have to find out. Declination angle we have to find out. And yes. So our angle, how we can find out? Based on cos alpha, cos inverse of minus 10 uh, latitude into 10 delta. Delta is again declination angle. Declination angle is also not given. That can be easily found out based on the number of the days. So once we know the declination angle and the hour angle, the latitude is given, so we can calculate the hour angle. So once we know the hour angle, we know the value of the omega s. Next, omega s we know, delta we know, and latitude phi is given, so we can calculate the value for the h naught. So the value of the, as now we know the value of the h naught, a plus b, the value a and b we know from this table, 0.28 and 0.48. Then S upon S max, the value of the S average is given 9.5, and S max we have to calculate. S max will be the function of the hour angle, 2 into hour angle divided by 15. So this way we can calculate the monthly average daily global radiation Hg, average Hg average, Hg bar we can calculate for any particular given location. So in this thing, we saw that the in solving the equation for Hg, we require the values for the regression constants a and b. So these can be calculated instead of looking in this table. These can be calculated empirically, and the empirical correlations are given. So empirical correlation, basically three things we should know. One is the latitude phi, that is already given. El is the elevation of the location above mean sea level, that will be in kilometer. And S bar is already given, and S max we know, that is the maximum sunshine hours. So that we can calculate based on the function of the omega s. That will S max is equal to 2 into omega x divided by 15. So similarly, we can calculate based on these three parameters only, we can calculate the value for the B1 also. So this is a general Gopinathan correlation. So let's see the problem. We have to again calculate the monthly average daily global radiation on a horizontal surface at Vadodara. The latitude is given during the month of March if the average sunshine hours per day is 9.5. So average sunshine hours is given, and here we have to calculate this using the Gopinathan's correlation. El, the elevation of the location above mean sea level is already given. So so that is given in meters. So we have to always put it in kilometer. Okay. So we will be calculate the value for the A and B. To calculate the value for the A and B, phi we know, El we know, S upon S max, S is given, S max we have to calculate using omega s. Omega s is the hour angle. Hour angle will again be function of the phi and delta. So delta is the declination angle, can be calculated based on the number of the days. Once the hour angle is known, declination angle is known, S max is known, we know the value of the A and A1 and B1. So we can calculate the H naught and then finally the Hg. Okay, then next comes So far we read about how to calculate the monthly average daily global radiation. Monthly average daily global radiation. So we have to be very careful about the terminology. So here the daily global radiation is asked. Next we are going to study about the monthly average daily diffuse radiation. So let's see how to solve problems for this. So again the formula is slightly different. The we have to calculate the daily diffuse radiation HD bar divided by Hg bar. Hg bar we have calculated previously. The daily G for the global radiation, that will be function of the S upon S max. So now again the problem is same, and we know the latitude, we know the value of the S, we know the value of the EL. We have to calculate the value for the HD bar. So for HD bar, first we have to calculate the Hg bar. To calculate the Hg bar, we should know the value for the correlation A1 and the B1. For values of the A1 and B1, what we need? We need latitude, the value of the psi we need delta, only latitude we need, and we need the value for the S max. For the S max we need the value of the WS. S max is the function of the WS, WS into 2 by 15, and WS is the function of the latitude phi and the declination angle delta. Delta can be calculated based on the number of the days n. So once we know the value for the Hg, then using this correlation, we can calculate the value for the HD, monthly average daily diffuse radiation. Now, first we read about the monthly average daily global radiation, Hg bar. Then we read about the monthly average daily diffuse radiation, HD. And before HD, to solve the HD, we need the value for the monthly average radiation on the extraterrestrial surface. Is that the extraterrestrial radiation? So that we need the value of the H naught. And after that, after calculating the daily global and daily diffuse radiation, we can calculate the value for the monthly average hourly global radiation. So hourly global radiation is function of Ig bar upon Hg. Ig is the monthly average of the hourly global radiation, and I naught is the monthly average of the hourly extraterrestrial radiation on the horizontal surface. Fc is the correction factor here. Omega again. Uh, this is the hour angle, and so we have to calculate the I naught. I naught is the monthly average of the hourly extraterrestrial radiation on horizontal surface. So that can be calculated based on the correlation with the solar constant. Again we need sine phi. Phi is the latitude is given, delta declination angle is given. So we should know only the n. For that, n is equal to I think the number of the day is given during the month of March, and the value of the n for that particular day will take. Then latitude, declination angle, and the hour angle. Hour angle will be based on the phi and the declination angle only. So, and another correlation is given to calculate the monthly average daily diffuse radiation. These are the first, the hourly global radiation, and then hourly diffuse radiation, ID. So that will be based on the hourly ID upon HD. HD is your uh, daily HD is your daily diffuse radiation. So yeah, based on this or up, then on again, um, to get the more accurate value, another correlation is given to calculate this. And the values for the A dash and B dash will vary based on the value of the HD divided by the HG. So let's understand these different values uh, using an example. So example is given that use the prediction equation to calculate the monthly average, hourly global and hourly diffuse radiation. So we have to calculate hourly global I, monthly average hourly global radiation IG we have to calculate one thing, and hourly diffuse radiation ID we have to calculate during the month of April on a horizontal surface. S, the value of S is given 8.6, latitude is given 28.35. So let's calculate. So first, what we need, we have to calculate for the declination angle. uh, Declination angle will be based on the n. The value of the n while calculating the average values will be for a particular month will be taken using the representative day for the particular month. For April it is 15th, and for others like for the June, May, and for these months the values can be followed as given in the problem or in the book in detail by the Sukhatme and Nayak. So once we will be having the value for the delta, then we can calculate the value for the hour angle omega s. So omega s will be the cos inverse of minus tan of the psi latitude into delta. Once we know the value for the omega s, then we can calculate the value for the s max. Now let's calculate the value for the h naught. H naught is again 24 into pi into I solar constant ISC into 3600 plus 1 into 1 plus 0.33 cos 360 by 365 into n. Uh, this will again the function of the uh, latitude, and 9.52 is your declination angle, and latitude declination angle, and the hour angle. The values can be considered using from the table or can be calculated. So once we know the value for the h naught, then we can easily calculate the value for the hg. When we know the value of the hg, then the correlation comes for the hd. So hd will be the how to calculate the value for the hd. Hd will be the hd of the value, the formula for the hd, the daily uh, the hd divided by hg. Monthly diffuse radiation divided by monthly global radiation is equal to this will be the function of 0.8667 minus 0.7365 s bar upon s max. S bar is given. S max, for this S max we need the value of the omega s, and as we calculate the omega s is 95.18, so it will be S max is equal to 95.18 into 2 divided by 15. So the S max, the value is 12.69 R. So once we know all these things, we will put it this in equation and we can calculate the value for the HD. And the value for the HD can slightly vary if we follow the other empirical equation. So once we know the value for the HD, now we have to calculate the value for the ID. ID is the monthly average. HD was the monthly average daily diffuse radiation, and now we have to calculate for the hourly diffuse radiation. Monthly average Hg is monthly average global daily daily global radiation, and Ig is the monthly average of the hourly global radiation. So now we have to calculate the value for the ID, monthly average of the hourly uh, diffuse radiation. So the correlation for the ID is ID upon HD is equal to I naught upon H naught. The value of the I naught we know, H naught we know, HD we know. Now based on this, we have to calculate the value for the ID. So the ID will be the function of the HD, Ig, and the H naught. So that can be calculated as 789 kilojoule per meter square per hour. So if we use another correlation, suppose this one, so the value may slightly be differ from the previous one. So these are the basics of the solar radiation on the terrestrial and extraterrestrial surface. Then first we calculated for the extraterrestrial, then terrestrial solar radiation. In the terrestrial and extraterrestrial solar radiation, we talked about the horizontal and the tilted surface, and we talked about the monthly average radiations. That will be the monthly average uh, daily global radiation, monthly average daily diffuse radiation, then monthly average hourly global radiation, and monthly average hourly diffused radiation. So these will help us in calculating the particular radiation falling over a surface for a particular time period. So in with the help of the estimation of the solar radiation over a particular surface, we can calculate the efficiency and the economic viability of our solar system. So that's it for the today's lecture, and we will meet in the next session. Thank you.